Master alcohols with these super easy reactions. I will also teach you two important maps that will help you to master alcohol reactions. First of all, we will learn preparation of alcohols. The first method to prepare alcohols is from alkenes. We prepare 1 degree and 2 degree alcohols from alkenes. To prepare 2 degree alcohols, we add water and H2SO4. Secondly, to prepare 1 degree alcohol, we add boron, hydrogen peroxide plus base medium. For example, consider this alkene and water. We know that water is a polar molecule. I mean, partial negative charge is present on OH and partial positive charge is present on H. On the other side, alkene has double bond. This double bond has 2 pi electrons. We know that pi electrons can easily attack on electrophile. Here, these pi electrons attack on this electrophile, hydrogen, due to which electron deficiency is created in alkene. This negative OH attack back, we get alcohol. Here, we follow Markovnikov's rule. Markovnikov rule states that hydrogen goes to the carbon having more hydrogen, while hydroxide ion goes to the carbon which has less hydrogen. This carbon has more hydrogen, so hydrogen goes to this carbon. This carbon has less hydrogen, so hydroxide goes to this carbon. As a result, we get 2 degree alcohol. Now I am interested to form 1 degree alcohol. To do so, I take alkene. I add boron, hydrogen peroxide and base medium. Due to addition of boron, hydrogen peroxide and base medium, it follows anti-Markovnikov rules. It states that hydrogen goes to the carbon which has less hydrogen, while hydroxide goes to the carbon which has more hydrogen. Thus this hydrogen goes to a carbon having less hydrogen, while hydroxide goes to a carbon having more hydrogen. As a result, I get 1 degree alcohol. This reaction is also called hydroboration oxidation reaction. Thus we learn that we prepare 2 degree alcohol and 1 degree alcohol from alkenes. Now we will learn preparation of alcohols using Grignard reagent. Remember that Grignard reagent is RMGX. We prepare 1 degree, 2 degree and 3 degree alcohols using Grignard reagent. For example, we prepare 1 degree alcohol from formaldehyde, we prepare 2 degree alcohol from any aldehyde, and we prepare 3 degree alcohol from any ketone. Now consider formaldehyde. We add Grignard reagent and hydronium ion to it. Here, RMGX provides alkyl R to this carbon having double bond, while hydronium ion provides hydrogen to this oxygen. Let me repeat this important statement. RMGX provides alkyl R to this carbon having double bond, while hydronium ion provides hydrogen to this oxygen. I get this 1 degree alcohol, where R is bonded to this carbon and hydrogen is bonded to this oxygen. Secondly, to prepare 2 degree alcohol, we take any aldehyde. For example, consider this aldehyde. We already learned that RMGX provide alkyl R to this carbon having double bond, while hydronium ion provides hydrogen to this oxygen. As a result, we get 2 degree alcohol, where R is bonded to this carbon and hydrogen is bonded to this oxygen. Thirdly, to prepare 3 degree alcohol, we take ketone. We already learned that RMGX provide alkyl R to this carbon having double bond, while hydronium ion provides hydrogen to this oxygen. As a result, we get 3-degree alcohol, where R is bonded to this carbon and hydrogen is bonded to this oxygen. Thus, we learn that using Grignard reagent, we can easily prepare 1-degree, 2-degree, and 3-degree alcohols. Now, the third method to prepare alcohols is from carbonyl compounds. We prepare 1-degree and 2-degree alcohols from carbonyl compounds. By carbonyl compounds, I mean aldehydes and ketones. We use mild reducing agent like sodium borohydride. We prepare 1-degree alcohol from reduction of aldehydes, and we prepare 2-degree alcohols from reduction of ketones. For example, consider these reactions. We use a mild reducing agent like sodium borohydride. This mild reducing agent provides 2 hydrogens, one to this carbon and one to this oxygen. As a result, we get 1-degree alcohol. Secondly, we again use mild reducing agent like sodium borohydride. In this reaction, this mild reducing agent provides 2 hydrogens, one hydrogen to this oxygen and one hydrogen to this carbon. As a result, we get 2-degree alcohol. Thus, we prepare 1-degree alcohol from reduction of aldehyde, while we prepare 2-degree alcohol from reduction of ketones. Remember that we use mild reducing agent like sodium borohydride. Now I will teach you one powerful map that will make preparation of alcohols super easy. We already learned that we prepare alcohols from 3 different methods. First of all, we prepare alcohols from alkenes. In this method, we prepare 1-degree and 2-degree alcohols. To prepare 1-degree alcohol, we add water and H2SO4 to alkene. To prepare 2-degree alcohols, we add boron, hydrogen peroxide, and base medium to alkene. Secondly, we prepare alcohols from Grignard reagent. Using this method, we prepare 1-degree, 2-degree, and 3-degree alcohols. We prepare 1-degree alcohol from formaldehyde, we prepare 2-degree alcohols from any aldehyde, and we prepare 3-degree alcohols from ketone. Remember that in these 3 reactions, we use RMGX and hydronium ion. Thirdly, we prepare alcohols from carbonyl compounds. In this method, we prepare 1-degree and 2-degree alcohols. We prepare 1-degree alcohol from reducing aldehyde. We prepare 2-degree alcohols from reducing ketone. We use a mild reducing agent like sodium borohydride. Thus noted down this important map which will help you to master preparation of alcohols. Now we will learn all important reactions of alcohols like reaction with hydrogen halides. For example, consider this reaction. We know that in hydrogen halide, halogen like chlorine is more electronegative. It attracts share paired of electrons. As a result, partial negative charge appears on chlorine and partial positive charge appears on hydrogen. On the other hand, oxygen is more electronegative than carbon, so it attracts share paired of electrons towards itself. As a result, partial negative charge appears on oxygen and partial positive charge appears on carbon. Now this hydrogen attack on this OH, we get H2O. Secondly, this halogen attack on this carbocation, we get alkyl halide. Now we will learn reactivity of alcohols with hydrogen halides, which is very important. The reactivity of 3-degree alcohol is very high than 2-degree alcohol. The reactivity of 2-degree alcohol is high than 1-degree alcohol. It is because 3-degree alcohols form stable carbocation, due to which it quickly reacts with hydrogen halide. Secondly, 2-degree alcohol forms moderately stable carbocation and its reaction has medium speed, while 1-degree alcohols form unstable carbocations, so their reactions have slow speed. Thus noted down this important point. Now we will learn reaction of dehydration of alcohols. It is super easy. For example, consider this alcohol. We add H2SO4 to it. Remember that H2SO4 is a dehydrating agent. I mean, it removes water from alcohol. For instance, it removes hydrogen from this carbon and it removes OH from this carbon. As a result, we get alkene plus water. Hence noted down this easy reaction of dehydration of alcohols. Now we will learn three most important reactions of oxidation. In oxidation of alcohols, we use two types of oxidizing agents. Strong oxidizing agent like KMnO4 and mild oxidizing agent like PCC. Now I take 1-degree alcohol, 2-degree alcohol and 3-degree alcohol. In case of 1-degree alcohol, I add strong oxidizing agent KMnO4 and mild oxidizing agent PCC. If we add strong oxidizing agent KMnO4 to 1-degree alcohol, we get carboxylic acid. Secondly, if we add mild oxidizing agent to 1-degree alcohol, we get aldehyde. On the other hand, if we add strong oxidizing agent or mild oxidizing agent to 2-degree alcohols, we always get ketone. Thirdly, if we add strong oxidizing agent or mild oxidizing agent to 3-degree alcohols, no reaction occur. Now here is one important question. Why 3-degree alcohols are not oxidized? To learn this question, first of all, we will learn oxidation of alcohols. For example, consider this 2-degree alcohol. During oxidation, hydrogen is removed from this oxygen, while alpha hydrogen is removed from this carbon. As a result, this 2-degree alcohol is oxidized. On the other hand, consider 3-degree alcohol. Here, oxygen will lose this hydrogen, but we can see that there is no alpha hydrogen present with this carbon. No alpha hydrogen means no oxidation. That's why 3-degree alcohols are not oxidized. Let's note down these important reactions. The last three reactions of alcohols are Lucas test. In Lucas test, we use HCl plus zinc chloride. For example, consider 1-degree, 2-degree and 3-degree alcohols. If you add HCl plus zinc chloride to 1-degree alcohol, no turbidity is formed. By turbidity, I mean solution becomes milky. It is like adding oil to the water. Secondly, if you add HCl plus zinc chloride to 2-degree alcohol, turbidity is formed in 3 to 5 minutes. Thirdly, if you add HCl plus zinc chloride to 3-degree alcohol, turbidity is immediately formed. Hence noted down these three important reactions of Lucas test. Finally, we will learn the second map to master all reactions of alcohols. If we add hydrogen halide to alcohols, we get alkyl halide. Remember that the order of reactivity of alcohols is 3-degree, then 2-degree, then 1-degree. Secondly, we do dehydration of alcohols. We add H2SO4 to alcohols. As a result, we get alkene because H2SO4 is acting as a dehydrating agent. Thirdly, we do oxidation of alcohols. I mean, using strong oxidizing agent like KMnO4 and mild oxidizing agent like PCC. If we add KMnO4 to 1-degree alcohol, we get carboxylic acid. If we add mild oxidizing agent like PCC to 1-degree alcohol, we get aldehyde. Secondly, If we add KMNO4 or PCC to 2-degree alcohol, we get ketone. Thirdly, if we add KMNO4 or PCC to 3-degree alcohol, we get no reaction. In case of Lucas test, 1-degree alcohol forms no turbidity, 2-degree alcohol forms turbidity after 3 to 5 minutes, while in 3-degree alcohol, turbidity is quickly formed. Remember that in these all three reactions, we use HCl and zinc chloride. Hence noted down this important map. Now we are going to master all 13 reactions of ethanol in one go. First of all, look at our hero on the board, ethanol C2H5OH. Everything starts with oxygen. Oxygen is very electronegative. It acts like a thief and pulls the shared electrons towards itself. As a result, oxygen gets a partial negative charge, while the carbon attached to it is losing its electrons, so carbon gets a partial positive charge. This carbon is an electrophile. It is electron poor and hungry for a partner. Now let's start with our first 4 reactions, where we kick out the OH group from ethanol. First, I take HCl and anhydride zinc chloride. The zinc pulls on the oxygen, making the carbon even more positive. Now the chlorine acts as a nucleophile. It has extra electrons and attacks that positive carbon. As a result, the OH leaves as water and we get ethyl chloride. Next, I bring in PCl5. It does the same thing but more aggressively. The chlorine attacks the positive carbon and we get C2H5Cl again. For our third reaction, I use thionyl chloride SOCl2. This is the cleanest way. The chlorine attacks the carbon while the other atoms turns into sulfur dioxide and HCl gas fly away. For our fourth reaction, I use hydrogen iodide with red phosphorus. This is a bulldozer reaction. The phosphorus has a massive pull for oxygen. It strips the oxygen away completely. The hydrogen then attacks the positive carbon. To sum up, the functional group is destroyed and we are left with a simple alkane called ethane. Now for the fifth reaction, let's try ammonia with zinc chloride. Ammonia has a lone pair of electrons on nitrogen, making it a strong nucleophile. Nitrogen attacks the positive carbon of ethanol. The zinc chloride helps kick the oxygen out. As a result, the nitrogen bonds to the carbon. We have now turned our alcohol into an amine C2H5NH2. Now let's shift our focus to the OH bond for our sixth reaction. I bring a piece of sodium metal. Sodium is what we call a super donor. It has one extra electron that it absolutely wants to give away. It sees that positive hydrogen and attacks it by throwing its electron. The hydrogen takes the electron and says goodbye. It leaves the molecule immediately to form hydrogen gas. The sodium takes its place. Now we have sodium ethoxide. This proves that ethanol can act like a weak acid. The seventh reaction is esterification. I bring acetic acid and a drop of H2SO4. In the acid, the carbon is very positive because of its double bonded oxygen. The oxygen of our ethanol is the nucleophile here. It attacks that positive carbon of the acid. The H2SO4 removes a water molecule. As a result, the two join to form a sweet-smelling ester called ethyl acetate. Now for the eighth and the ninth reactions, we look at the temperature trap. I take H2SO4 and heat it to 413 Kelvin. At this lower heat, one ethanol molecule acts as a nucleophile and attacks the positive carbon of a second ethanol molecule. They join by an oxygen bridge to create an ether. For the ninth reaction, I turn the heat up to 443 Kelvin. Here, sulfuric acid acts as a dehydrating agent. I mean, it removes water from ethanol, due to which a pi bond forms between the two carbons. To sum up, at high temperature, ethanol becomes ethene. For 10th and 11th reactions, let's look at oxidation. I take an oxidizing agent. It pulls two hydrogen atoms away. This creates a double bond with oxygen. The molecule becomes acetaldehyde. If we add more oxygen, it climbs the ladder to become acetic acid. I mean, it is a step-by-step transformation. For the 12th reaction, I use copper at 573 Kelvin. The copper surface acts like a magnet that pulls the hydrogens off. As a result, hydrogen gas is formed. It gives us the same acetaldehyde very quickly. Finally, the 13th reaction is the iodoform test. I take iodine and sodium hydroxide. The iodine attacks the carbon next to the OH group and replaces its hydrogen. This makes the molecule unstable. The sodium hydroxide then attacks the positive carbon and the molecule breaks apart. As a result, a bright yellow solid called iodoform is formed. It is a test to identify ethanol in any liquid. To sum up everything, every single one of these 13 reactions is just a story of charge. The oxygen pulls, the carbon becomes partial positive charged, and a partner attacks. In the next lecture, we will learn all about phenols.